Hello and welcome to an A2 AQA physics revision video, or topical video, or whatever it is. This is the first video of radiation, okay, and obviously radioactivity. In this video I'm just going to be going over the Rutherford experiment. So as I said, something you probably should have covered at GCSE, but really I'm just going to spend a few minutes refreshing your memory, because it was a couple of years ago if you received A2. And then I'm going to go and look at something called the Gieger tube. Now obviously this is a device which measures radiation. I'm going to go radioactivity, same kind of thing. And I'm going to be explaining how it does that, and what actually it's sort of made of inside, really, because you may have been told there's a Geiger tube that measures radioactivity, but how does that happen? So we're going to look at that, and maybe I might have done that before, just by explaining the Rutherford experiment. I'm going to look at the types of radiation, and again I'm going to be looking at putting the radiation through a magnetic field, which is something you may have done at GCSE, but as I said, we're going to go over it anyway. Then we're going to be looking at something you definitely won't have looked at GCSE, which is radioactive decay. Now obviously you all know that radioactive sources decay. That's why they're radioactive, because it's an unstable nucleus that decays, okay? It's radioactive. Right? And then I'm going to be looking at the intensity of the radiation. What do we actually mean by that? So you can use the same kind of principle when we looked at doing the intensity of, I know it's a totally different thing, but when we looked at the intensity of the photoelectric effect, I know it's slightly different, but radiation is emitted through photons, really, so it is quite similar. So we're going to be obviously talking about that. And then I'm just going to be talking about the N to Z plot, so the neutron to nucleon Z plot, or proton to neutron plot, where we're going to be looking at some curves and what happens, what atoms are stable, what atoms are not stable. Then I'm going to be finishing off with just showing you really what happens. As I say, it's a small recap at the end of the decay process, in terms of what actually happens to the nucleon and proton number, which you should all be familiar with, obviously. Okay, and I might go over, because obviously we're going to be looking at certain types of decay. I'm going to be looking at beta minus and beta plus decay, just giving you a bit of a recap that probably somewhere throughout. But if you're not comfortable on that, please do put in the comments below, and I will try to get a particle video up on that shortly. But for the moment, I'm hoping you understand that what beta decay is. Okay, so I'm going over that in a bit. Right. So the first thing I said I was going to kick off with is the Rutherford's experiment. Okay, so to understand why he did this, obviously we need to go way back into pre-Rutherford experiment, and what they all thought was we had the atom look something like this. Where we had the pudding, okay, which was all it's called the plum pudding model, and all of the all of the atom was positive, and we had dotted negative charges just around. Obviously they didn't know about energy states or anything like that back in these days, and they were just dotted. The reasons, the negative charges, the electrons, but obviously they didn't know that, they just knew the negative charges, okay? They were dotted around somewhere around the atom, okay? And all of it was positive. But what Rutherford did was came along and did the experiment, hoping to prove this model, but obviously instead he found something else. Okay, so essentially what we have here is, in his experiment, we had the emitter of radioactivity, right, and we had the foil, alright, and obviously you had someone here watching where it was deflected from. Okay, so again, I'm terrible at art, so hopefully you can excuse that. Alright, so you've got someone there looking at the source. Obviously this is in a vacuum. It was in a vacuum because we don't want the alpha particles, which is what's being emitted here, being deflected before it hits the gold foil. Okay, and what essentially happened was, obviously some of them were deflected straight back. The ones that hit, I think it was 1 in 10,000, and so 1 in 10,000 atoms were deflected. We're going to go on to look at this in a bit more detail in a minute. But really what happened was, obviously some of them just went, were deflected slightly, some of them went through, and some of them went straight back. And it couldn't, why would it come straight back? I think one of the famous quotes is, it's like throwing a naval shell at a sheet of paper and it bouncing back. That's how astonishing they found it, okay? Because they weren't expecting it to come back at all, especially straight back. Alright, okay. So hopefully that makes some kind of sense. As I said, it's just a recap of what you did at GCSE. Now, I said we're going to look at this in a bit more detail. Now, we said that 1 in 10,000 atoms or alpha particles were deflected. Okay, now we need to. This gold foil is one unit layer thick, and that's because if we had more than one unit layer, the atoms would be deflected more than once, and we wouldn't be able to tell exactly where the atoms, what had deflected it, or if it would bounce off from the particle in the atom, in the gold foil. Sorry. So obviously that's why we had that. Now, to be able to work this out, we need to. Because we've got an area of the gold foil, and we've got the area of the individual atom that we're firing it. Okay. And obviously they have some kind of a relationship, because obviously the bigger the area, the greater the deflection is going to be, okay? Because the more likely to be deflected, whereas, if it's a small area, less likely to hit it, okay? So hopefully that's explained it. So what we need to do is we've got some kind of ratio here. Okay, so the area is a half pi r squared, or a quarter d squared, okay? So a quarter little d squared, which is the little d is the diameter of the nucleus, or the atom that's hitting it, okay? And the one on the bottom is going to come in the same area, half pi big D squared. The big D represents the diameter of the mass, or sorry, the thing that is being deflected by, okay? So this is the gold foil in this case, and that's equal to 1 over 10,000 n. Now I must stress at this point, what we mean by the little n is it's the number of atoms that are being fired at it, okay? Because we said 1 in 10,000 n are deflected, okay? What that means is if there's 1 n, okay, then 1 in 10,000 will be deflected. But generally, there might be something such as the number of atoms might be 10 to the 4. Okay, it might be 10 to the 4 alpha particles, because as I said, they're very small, so you could have a fairly big number. And you can clearly see these pi on 4, or quarter pi, they cancel. So what we're left with is little d squared over big D squared is equal to 1 over 10,000 n. And because we said n is 10 to the 4, it's 10,000 times 10 to the 4, which is obviously a very big number. Then what we do is we rearrange this to get the diameter of the alpha particle, or whatever you want to do, okay? So little d squared is big D squared times both sides by big D squared over 10,000 times 10 to the 4, okay? And then you would square root that to get the diameter of the atom that has been deflected, okay? So, as I said, hopefully that makes some kind of sense. Really, that would just be the method that you would use to work out the diameter of what's been deflected. But, as I said, it's really just comparing the areas more than anything. And we can use this idea later on when we go to look at obviously comparing the area of the foil to the area of the atom that's being deflected, okay? We're going to look at that in a slightly different way a bit later on. But for now, that's all I'm kind of expecting you to know. As I said, most of that, apart from this little equation we've done here, is given in your form sheet. You should probably have gone over that at GCSE, but as I said, most of this topic is just refreshing GCSE memory. Okay, now what we're going to go and look at is the types of radiation. And I'm going to put them through this magnetic field. Now, as I said, you may have done something like this at GCSE. So what you've got here is we've got 2 magnets and we're passing radiation through. Now the first one I'm going to pass through it, I'm going to draw by just a straight single line, okay, and this is gamma. And gamma just goes straight through it and it's not affected by the magnetic field. Alpha, okay, that's the most deflected. So I'm going to draw that as a squiggly line, bouncy line even, and that sort of goes straight like that, okay, so it goes straight bend Whereas beta, okay, it's the only one we've not done, I'm going to do that by the dotted line, is still deflected, but not as greatly deflected as alpha. Okay, now we can see these two are going in a circular path. Okay, and that is because obviously they've got a mass and they're a flow. It's essentially a flow of charge. These two. Well, beta's more obvious a flow of charge. Okay, so it's obviously it's electrons sort of thing. Right. Now, because they're going in a circular path, we can apply our knowledge of F equals mv squared over r. Okay. If we want to work out the radius of these two, because obviously if we let this go, if we continue going in a circular path, okay, such as in the cloud chamber, which we're going to look at in a minute, which probably should have left this too, okay, it's equal to r is equal to mv squared over f, and obviously the greater the radius, the greater the mass, the greater the velocity is increases the radius. Okay, so obviously you get bigger curve with a larger mass. Okay, now the reason why lambda is not deflected, well, it doesn't follow it doesn't have a mass, because well, it does, but it's a very, very insignificant one. It's because it's made up of photons. Remember, gamma is just made up of photons, which is electromagnetic waves, which really don't carry any mass. Okay, so hopefully that makes, as I said, kind of covers something. What I want to do, as I said, I was going to really save that for the cloud chamber, but so we'll go over that in a minute anyway, because it's not too much of a difficult thing. Okay, applying to the cloud chamber. Actually, I just mentioned that now. Okay, so the cloud chamber really is just gas at very low pressure, and we get the same kind of principle. Okay, so we get a straight gamma line. Beta is deflected the most. So it's just like this, but in the cloud chamber really. And a cloud chamber is just it's a gas at very, very low pressure. So it's it's quite spread out sort of thing. Okay. Hopefully that, as I said, that you can see the distinction between the two. They're quite similar. Alright, what we're going to do now is look at these individual radiation. Now I said, obviously, you've got alpha is 2 protons, 2 neutrons, and your beta is sort of your electron kind of thing, and your lambda, which is obviously represents gamma, is made up of photons, so it doesn't have a mass, so it can't really be deflected. That's why in both of these situations we see a straight line. But what we're going to look at now is the actual properties, in terms of what is stopped by each radiation. Okay, now, as I said, I'm just going to draw a little kind of sketch, really, table. So we've got the type of radiation, and obviously we've only got these 3 types. Okay, so we've got alpha, beta, and gamma. So I'm going to put ionizing, sort of level of ionization. So ionizing, so the ability to ionizing, moving or gaining electrons from another atom. Alpha is the most strongest, so alpha is the strongest. Beta is the weakest, and the weakest ionizing out of the 3. And lambda or gamma radiation, is somewhere in the middle of alpha and beta. Okay. Now, as I said, you can look at this. You can actually compare this in terms of. Okay, so hopefully, as I said, that makes some kind of sense. All right, so what I'm just gonna recap now is something you probably should have known at GCSE. Oh, sorry, I do apologise. I've got that wrong. Damn it. At least I spotted it. I didn't think I got it right, that's why I looked to the side. So I do apologise, I shut myself up. Okay, so alpha is the strongest ionizing, but beta is somewhere in the middle. I didn't think that was right because of the method I used to remember it in my head. Okay, and gamma is the weakest. Do apologise. So, just to recap, this is the right way, so I've just recap my sheet. Alpha is the strongest ionizing, beta is the middle in terms of ionizing, and gamma radiation is the weakest. So that is the correct one, ignore what I said before. Alright, so we need to look at what these individual radiations are stopped by. So alpha is the strongest ionizing, but it's stopped by almost everything. Okay, it technically isn't stopped by air, although if you try to travel quite a long distance, it would stop, obviously, because it can't go that far. Alright? and it's obviously there for, so it's technically not stopped by air, but it really is. Okay, it's stopped by aluminium, therefore, and obviously lead. Okay, but beta being in the middle, it's stopped by only, sorry, beta stopped by, oh great, I've forgot to include another column. Okay, so after air, please include another column for paper. I do apologise. Right, so obviously alpha is stopped by paper. Beta can go through air, paper, but it can't go through aluminium or lead. Gamma, on the other hand, well, it just continued going straight through pretty much everything apart from lead. All the way around. Tick means it can go through. Cross obviously means it can't. Okay, so alpha's strongest ionising, but it can't go through anything other than air. And it can't really go through air, but it can for a short period. So we class it as being able to travel through air. So what we can see here is the stronger the ionising the radiation is, the less it can go through in terms of what it can actually, materials it can pass through. Gamma can pass through pretty much everything apart from lead, but it's the weakest ionising, and this is obviously because, you know, if it's the strongest ionising, it's going to ionise something first and therefore not be able to get through it without being ionised. So it's no longer alpha, beta, or gamma radiation. Okay, so hopefully that makes some kind of sense. All right, so if you just remember that alpha is the strongest, beta is the middle, and gamma is the weakest. You could do it in terms of the alphabet, you know, if you wanted to. I'm saying you could. So the closer the letter is to the start of the alphabet, the more ionising it is. So obviously alpha is for beta, so obviously therefore it's stronger than beta, and gamma is really near the end, so it's obviously the weakest. And you also have to remember the stronger the ionising material is, the stronger the ionising radiation is, the less it can pass through as well. But as I said, it'd be quite good just to remember that kind of table, but if you can't, don't get too fussed about it. Alright, so now we've looked at the types of radiation, what we're going to go on to now is looking at something called the Gieger tube. Okay, now you may have heard Geiger counters. These are very similar things. Obviously they contain a Geiger tube within them. So we're going to look at actually what a Geiger tube is. Now, obviously because we're looking at radiation, it's going to be something to do with counting radiation. But I'll just draw a quick sketch on the board for you. Okay, so we've got a positive, we've got it's been plugged into the mains of 450 volts, just say. Alright, it's just a quick sketch. And then the other, there's nothing coming out of it of 0 volts. Right? And if we break this up, so if we draw a little sketch of what's happening inside of this, okay, what we've got is a anode which is going through it, okay, which is obviously a positive charge, and then inside the Geiger tube we've got particles of argon gas, which, if you look in the periodic table, is in group 8, which means it's obviously got a full shell of outer electrons, so it's quite a stable gas, okay? And obviously that's at low pressure as well. Now at the front of this, what I've tried to draw here is it's obviously sort of curved like this, right? And we've got sort of a slight hole, a slit, if you want, in the front of this, okay? So a small slit, if you want to call it that. And this allows your alpha, beta and gamma to pass into the Geiger tube. Okay? And when the particles alpha, beta and gamma pass in, okay, obviously all can, when they pass in they ionise the argon molecules, or argon gas molecules, okay? So they enter, so radiation enters and ionises the argon gas particles. When it ionises the argon gas particles, it gives an electron, okay, so that obviously turns it negative, so the argon gas becomes negative, and it's obviously an ion now, and this is therefore attracted to the positive anode, and if subtracted the positive anode, this causes, because this is essentially a current now, we've got a flow of electrons, okay, so it's a current, this increases the ions in the current, okay, so that obviously therefore increases the current, and that's obviously if there's an increase in the radioactivity, okay. Now, obviously this is put into the some kind of formula to work out, well, how much is the radiation changed by, and we can work this out because one of the things that you need to know about counts is that the current is proportional to the activity, which is something we're going to go into in a minute. So if you just learn that, put that down, current is proportional to the activity of the substance, which is just the decay of it really, but as I said, we're going to go into that in a minute. So current is proportional to the activity, okay, so therefore it's obviously directly proportional, so current is equal to K constant times the activity, okay. And obviously it'd be negative Ka because we're obviously going to be decreasing, but just Ka, okay. So hopefully, as I said, that makes some kind of sense. Don't get too worried about the fact if you don't know what activity means just yet. We're going to go on to that in a second when we go to look at radioactive decay. Okay, so what we're going to do now is, as I said, just going to look at that radioactivity decay. Radioactive decay. Decay? God's sake, which says long day even. It's only just started. I'm so stuffed for today. Anyway, going back to this. Right, so what I'm going to look at now is radioactive decay. Now, one thing that you need to know straight away is radioactive decay is exponential. Just going to rub this off. You can go back a few seconds and copy it all down if you didn't get that. But I'm sure there's diagrams online or whatever you get these days. Okay, so it's exponential, so we have to draw some kind of exponential graph, and on the y-axis what you would draw is the activity. Okay, so this is the counts per second or whatever you want to say, and obviously this is the time in seconds on the x-axis. Right, now the reason it's exponential is because we have something called a half-life. And a half-life is the amount of time it takes for a substance to decay by obviously half of the quantity. But the time taken for half of the quantity of a given substance to decay, that's kind of the definition if you want to take one down. And why does this give us an exponential curve? Well, it gives us an exponential curve because, as I said, half of a given quantity of substance to decay. And obviously if we half that substance and half it again, the change is going to be different each time, okay? So if we look at this, right, we pick out, say this is 100 counts, and we go down to 50, okay, the time difference between the two is the same as going from 50 to 25, okay? So that obviously gives us this kind of curve, which obviously leads us to think, leads us to show us that it's some kind of exponential curve, okay? Now, that's really why it's an exponential. We're going to go on to looking at that half-life stuff in a little bit more detail and how we come up to the equation. Now, I'm just going to tell you the equation for half-life. So I've got T subscript a half, which just means half-life, is equal to ln2 over something called a decay constant. Now, as I said, I'll go into that in a minute in terms of how we derive that. I've not just made it up, but you don't need to know how to derive it. It just comes from an equation that we're going to come to in a minute. Okay, so what's the decay constant? Well, the decay constant is sort of like the gradient. So if we redraw this curve, okay, and if we just draw a sort of a tangent to that curve at a given point, at that point, that is the decay constant. Okay, and obviously, you know, it sort of it doesn't change for a certain substance, but it will affect it at different points. Okay, it'll just be going through it at different stages. So over here it might be something like that. Okay, and over here it might be something like that. We will get the same gradient, so we'll get the same decay constant. Hopefully, so you get that. But if you don't worry about it because it doesn't really matter. Now, there's no other way of starting the equations for this. First thing I want to do is talk about activity. Now, we said activity was, the current was proportional to the activity. Okay, we were looking at the Gieger tube. Okay, but what actually is the activity of a substance? Well, the activity of a substance is just the decay per second kind of thing. Okay, so if it's the decay per second, the decay is measured obviously in the change of the a given quantity of the substance, so changing the number of molecules, really. So it's a change in the number of molecules over the change in time. Sorry, I don't know the way to build this up, but the change in molecules, okay, so if we write delta n somewhere else, is equal to lambda n delta t. Okay, lambda being the decay constant and delta t. And I have a go at explaining that, but as I said, if it doesn't make sense, it doesn't really matter, because all we need to work out is the last equation, which are given in your formula sheet. Now, the change in the number of molecules, well, if it was just obviously, changing the number of molecules is the change in molecules per second, or the number of molecules times the time. But if we just did the number of molecules times the time, we'd be increasing, but surely we need to be decreasing it, okay? And the decay constant, obviously, we put a negative decay constant in there because we're decreasing. But we're assuming the decay constant it is kind of a constant proportionality. That's the only way I can really explain why we have this. But anyway, when we put this equation in, okay, for delta n, we put lambda n delta t, and I've changed it from a negative, but as I said, it doesn't really matter, over delta t. Delta t's cancelled, so we get A is equal to lambda n, or in other words, the activity is equal to the decay constant times the number of molecules. So that's how we come up with the activity formula. Now, I'm going to mess with your brain a bit. The change in the activity, okay, is equal to the decay constant times the number of molecules over delta t. You're thinking, how do we come up with that? Well, when we do the change in the activity, we're doing that over a change in time. Obviously, we have to take into time as a considerating factor. And when we take in time as a considerating factor, we've already done it over here. So it's essentially delta t times delta t on the bottom. And obviously, only one of the delta t's cancel. Right? So we're left with this over delta t, which is exactly what we've got here. So hopefully, you'll be able to get that. Now, there's one thing that I want to just mention here. There's what we're going to be, because obviously this is an exponential. The only thing that we've done so far in physics that is exponential is capacitors. And when we looked at capacitors, we said that the final charge, the given charge that you want to find out is equal to the initial charge, Q0, times e to the negative power of negative t over RC. RC being the time constant, okay? And what we said was when the time constant was equal to RC, we had e to the power of -1, which if you work it out is 0.37, okay? So therefore there's a 37% difference in the charge, okay? So for every time constant there's a 37% difference in the charge. And because it's an exponential, we'd need 5 time constants to totally discharge it. And this equation, remember, only works for discharging a capacitor. So how the hell are we going to relate this to what we currently be doing? Because clearly this is not about capacitors. Even though we've still got an exponential graph, yes, that's the only real similarity. There's no obvious connection between the two. Alright, so don't know really how to come across this, but alright, so say we'll use this as the activity, okay? So the activity is equal to the initial activity times e to the power of negative lambda t. So that's the equation for the activity, okay? The number of molecules equal to the number of initial molecules times e to the negative lambda t. And the same principles apply, sort of thing. Okay, so we've got the initial value. You can see how they're closely related. Instead of negative t over RC and negative lambda t, they are closely related. But as I said, that's just a formula that you need to be able to apply. Really, there's no way that we can. I mean, I'm not going to show you how to derive that formula because, well, I don't know. But it really just comes from A is equal to decay constant times n, and it's a case of times modifying it so it becomes A is equal to A naught times e to the power negative lambda t. Oh, sorry, it doesn't come from that, I do apologise. It comes from the first equation that we did. So delta n, so changing the number of molecules equal to lambda, negative lambda n times delta t. And what we essentially did there was sort of e to both sides sort of thing, and came up with this formula. Okay, so you can see obviously these two ends would cancel, sort of thing. If you divided them both by n, obviously therefore that would leave you with 1 or the official number of molecules. Okay, and then that would be equal to negative lambda t e both sides, and you would end up with this equation. Alright, so hopefully as I said that makes some kind of sense. But I know we said the activity curve here is sort of exponential, but we can never actually predict which thing is going to decay next. So we can't say, oh well, this molecule is definitely going to decay, because yes, it is likely to decay, but we don't know it definitely will do, obviously, because things can change. Alright, now one thing I just want to go into now is coming up with this half-life equation. Now, as I said, you don't really need to be able to show that you know the workings for this, but you do need to be able to apply the function. Welcome back. Sorry about that. Just camera sort of well, ran out of battery, and rather embarrassingly, carried on talking. Didn't actually realise the camera had stopped. Anyway, so hopefully I don't start talking about something I wasn't. Okay, so all you really have to do with this is just use the formula. You don't really have to come up with you have to explain the way you derive it, because it's not in the specification, so it'd be a bit mean to ask, but obviously it's nice to be able to know these things. Okay, so let's assume a couple of things. I'm going to put a couple of assumptions out there. Really, we're going to be using this equation over here. So at time t0, see the initial, before there's any decay, let's assume that the number of molecules n equals n0, okay? So over here where we've got n, we'll let that equal n0. I mean, I know we've got n0 over here as well, but we're going to be using that to our advantage. And when there's a half-life, okay, so t subscript to half, there is half the number there originally was. Now we could put half times n, but I'm going to put a half times n0, because obviously it's going to help us when we try to simplify it. But it doesn't matter, you could put either. And you could change that to n if you wanted to, but whatever. Okay, so let's put in what we currently know. Okay, so when t equals a half, there is 0.5 times the original amount of molecules. Okay, so going on from this equation, right, what we're going to do is 0.5 times n0, which is half the original because it's half-life, is equal to the original times e to the power of negative lambda, and we're going to put that t subscript to half there because it's the half-life, so half. So there's obviously a time that's passed, okay? And we just label that. You could put that as t, but I put it as t to the half because we want it, and I'm going to show you that we can get this. Obviously you could work backwards from that, but this is the way to do it. Okay, what we're going to do is divide both sides by n0. In other words, they cancel out. So we're left with 0.5 is equal to e to the power of negative lambda t to the half. And what we're going to do now to get rid of this e, ln both sides. So therefore we're left with ln of 0.5 is equal to negative lambda t to the half. Now, because we've got a negative here, we obviously want to get rid of this negative, because if we divide both sides by a negative lambda, okay, we'd end up with t being a negative figure. Well, I don't think so actually, unless I'm talking complete and utter rubbish. ln, sorry. Double check. Yeah. Well, no, sorry, we'd end up with a positive number. But because I don't really like having, it looks like it's going to be negative time. Obviously it isn't, because negative ln a half is negative something. Because ln of a half is the same as ln of 2, okay, therefore we could just change this to ln of 2. Because, well actually it doesn't really matter, as I said, this is also therefore equal to ln of a half over lambda, over negative lambda, sorry. So you could either have one of them two. So what I'm going to do is sub in ln of 2 in here, right? So that's ln of 2, and then we're just going to ln of 2 equals lambda t to the subscript of half, rearrange to get t, and you should get the equation above. Alright, so that's pretty much how you derive that equation. As I said, it's not really required in the specification, but it's always nice to be able to explain it, okay, if you do need to build it up from somewhere. Not that you would, but just in case, okay? Right, so that's the half-life equation. Just want to mention intensity now. Now, intensity is, when we were looking at it way back in AS, we were looking at the intensity of radiation, of incident light, sorry. We're changing that, or we're changing the number of photons that arrive per second, okay? But obviously radiation, we're talking about the radioactive energy here. Now we said energy from radioactivity is sort of produced in photons, so to speak, okay? So I'm just going to, because I don't want to get rid of all of this, it's just a little thing. Alright, so basically, intensity is the energy that passes through, energy per second that passes through a given area. Okay, or sorry, it's the energy that passes through a given area. Okay, that's the intensity. Now the energy, as we said, is made of, the radiation is made of photons essentially. So it's HF, but we obviously have more than one photon, so it's NHF over 4 pi r squared. Okay, and that is because when we did the charge, because this is quite relative, at the start probably should have mentioned the charge equation, the force between two charges. Sorry. When we were looking at electric fields, we came up with that charge equation, which was the constant was 1 over 4 pi r squared, or epsilon naught, I think it was. I can't remember. I lose track of stuff. Okay, so you can kind of relate it to this. Well, obviously NHF is going to remain the same. 4 pi is going to remain the same. So the constant is 4 pi. Sorry, NHF over 4 pi. But honestly, the thing that changes is r squared, and r is not the radius; it's the distance. So really, you could label it as d if you wanted to. So let me just double check what the distance is before I tell you something that's wrong. Nope, not there. Do apologise. Probably should have looked in this book. Sorry, I do apologise. So I'm saying r is the distance. It's the distance the photon has to travel. I apologise. Yeah, I'm not making this very good, am I? Yeah, I really did think I had it straight away. I was going to go, yes, Sam, this is what it is. And I'm wait. I could have looked it up, but I was pausing the video, but obviously not. Right, here it is. Okay, so r is the distance from the source. Okay, so it's it is the distance a photon has to travel, but really it's the distance from the source. Alright, so that's essentially the inverse square law of radiation, which is something you might have done at GCSE, but you might have not looked at it in that detail. Okay, you might have just said, twice the distance, the intensity divided by 4. That's kind of what we're looking at here. Alright? So really it'd be k over r squared, okay? So I is equal to k over r squared, and that's the inverse law, inverse square law of radiation, because if the intensity increase, you can apply it to the situation. You'd have to tell you. Alright, hopefully that made some sense. Right, now what I was going to do is just look at the NZ plot, so the neutron and the proton number. But I'm going to say it's going to be a bit of a challenge. Really, it's not that too big a deal. Just whether debating whether to actually do it or not. Right, well, I'll just pause the video actually, and I'll do a sketch of it, because I don't know. So it's going to take me a little while to try and sketch this. So I'm just going to sketch it on the board, go back to doing this video, and then we'll talk through it. So actually, contrary, on the opposite to what I wanted to do, I'm just going to rub all of this off and just draw this diagram. Well, the reason is because, well, you don't need all the board space, and second of all, I could be bothered, but obviously the first point is more important, obviously. Okay, and obviously so keep your mind in this. Right, so what we've got here, this is the NZ graph. In other words, the number of neutrons on the y-axis and the number of protons on the x-axis. And we've got two lines here, okay? So all these little x's, if you can quite make it out, but follow this line. In other words, the line follows the points, okay? So like a line of best fit, really, just hand drawn. Right? And this is all the individual points where the current atoms that we know. Obviously, not every single one, but you get the idea, okay? And they all follow this kind of same pattern. The number of neutrons increases, and we can have a few more neutrons. The ideal is somewhere between these two, by the way. But all of them are stable, okay? Really, what we want is somewhere in between these two. Now, the one on the right-hand side that sort of goes more towards the protons, that is unstable. So basically, any point that's on this line will try and get back to the stable nuclei line, okay? In other words, it will try to get rid of a proton. And if it tries to get rid of a proton, it will change it into a neutron. And the only way it does that is by beta minus emission. So, just let me double check that it's definitely beta minus. This is how bad it's got. I do apologise. Yeah, so it will emit the beta minus particle, okay? I really don't think that's right. Sorry, beta plus, I really don't think that was right. I don't know what's going on with me today. Okay, so beta plus, we'll get back to that line, because a beta plus changes a proton into a neutron, okay? So that's beta plus changes a proton into a neutron and emits a positron, okay, in the process as well. But really, what we do is they will always be beta plus emitters if they have more protons than neutrons. Because they want to get back to the stable line, and obviously vice versa if they're too far, okay? Now, this kind of leads us to say, well, if an atom has a few more neutrons than protons, it is stable. But if it has a few more protons than neutrons, it's not stable. Okay, so that's really what this NZ graph is showing. I do apologise about getting my beta plus and minus mixed up. I do need to obviously look at that again. Alright, so I'm sorry for spending most of my time over on the left-hand side of the video. That's because obviously there's quite a lot of information that I don't want to keep standing in the way of on the board. Alright, so thanks for watching. Hopefully, you've been able to follow it through. I think there'll probably only be one or two more videos on nuclear physics after this, which will just be on. Oh, actually, there's one more thing. Sorry, I just want to get. I was actually just going to mention how if an atom emits an alpha particle or emits a beta particle, what effect that has on the atomic numbers and stuff. But really, I don't want to waste too much of your time doing that. Obviously, if it emits a beta, if it emits an alpha particle, it's going to emit the atomic number of 4 and the proton number of 2. Okay, obviously 2 protons, 2 neutrons. Therefore, you can see where it would move in the actual periodic table. Okay. So hopefully that makes some kind of sense. There's nothing more than that you would put on that. And then in the next videos, we're just going to be looking at nuclear radius, nuclear density. It's quite related to that thing we were talking about by looking at comparing one area to another, but we're going to be sort of looking at it in a slightly different way. And going back to our good old friend, the de Broglie wavelength, which we used just off the wave-particle duality in AS physics, okay? Obviously, acts as a particle or a wave. We're going to be looking at binding energy, nuclear energy, mass, fission, fusion. So again, a mixture of A2 of expanding on GCSE. That's because we obviously didn't do nuclear physics at AS. As you can quite see, you would have needed exponentials, and you wouldn't have done exponentials in your first year unless you were really, really smart. Or just weird, just whatever. Okay, so thanks for watching. Hopefully I've not been too boring and stood at the side. Normally I'm waving my arms about famously and probably punching the camera over in one of my next videos. But do stay tuned for that, okay? So that's something to look out for. Alright, so thanks for watching, and we'll see you in the next video.